Welcome to Waterloo Laboratory. Here we can find Krysta and her research group formed by Michael Friedman, Sankar Das Sarma and Chetan Nayak, who are engaged to quantum architecture and computation in Microsoft Research. People think that this was first thought by Krysta about 3 or 4 years ago, but the truth is that it is much older, when she did her PhD. Krysta graduated in mathematics and computer science, and she is pioneer in the quantum field. She and her team want to demonstrate through quantum algorithms applied to real quantum devices that the quantum computation is the future in computation. Lately, some news and articles about quantum computing have made the front pages, as for example, the news about Google Quantum Computer, the quantum chip helps crack code, or the infinite machine. This research group tries to explain issues that are not possible to be solved by classical mode, and we need quantum computers to solve them. Microsoft Research Group has for sure that quantum computation will transform the digital. Straight away, we are going to listen to this research group discussing about the next revolution in computing and how to solve the digital computers' problems while they do their job in laboratory.
Okay guys, I'm going to the laboratory. I'll wait for you there.
Okay Krysta, see you! Well, can you explain to me why we need quantum computers if classical computers are improving very fast? Surely, in a short time, a classical computer will do what a quantum computer does and more.
We know from Moore's law that the number of transistors on a microprocessor doubles every 2 years approximately. But recently, this time has been getting slightly bigger due to technological limitations, slowing down the progression. And even if we could power all the microprocessors, there are some problems that are not solvable with our classical computers. We call them intractable problems, and we need to look for new methods of computation so we can keep improving the performance of our computers and so we are able to solve these problems. One of these intractable problems is the RSA 2048 problem, which is an encryption method used for online shopping among other fields, and it is unbreakable with a classical computer because we would need billions of years to solve it, while we know that it could be solved in a matter of seconds with a quantum computer.
Ah, okay, I can understand why we need quantum computers now. Let's go to see what is doing Krysta.
Hi again guys.
Hi again Krysta. We were talking about why we need quantum computers actually.
Okay, everything we talk about sounds great, but I think it's necessary to remember the basic principles of quantum mechanics, such as interference, our friends qubits, the superposition, and finally the entanglement. As we well know, interference is created when particles are launched through two slits and they are built up one by one, becoming an interference. It demonstrates the wave-particle duality. As well as, these particles are able of passing through both slits at the same time. We call superposition to this phenomenon because a qubit can have two simultaneous states, 0 and 1, before its collision, which takes place when an observer comes on the stage. So, the particles only pass through one slit, like we can see in the following image. Finally, let's talk about interlacing, which means that two interlaced qubits share properties with each other. What does it mean? It means that if they become separate, what happens to one will happen to the other. A clear example of entanglement is Bell states.
But what's the catch? This is not as simply as we have expected it to be. We need to control that system. Moreover, we need to have in mind that these systems want to remain in the vacuum and not interacting in the classical world. So every time we do a measure, we are introducing errors as they are losing its properties. That is what we call the coherence. In addition, we have to bear in mind the requirements for the quantum computation, which are the quantum algorithms, the quantum hardware, and so forth. But these quantum algorithms already exist, although they are not 100% quantic, as for example, the quantum simulation in 1982, the Shor's algorithms in 1994, or the solving linear systems of equations in 2010. These algorithms consist on some matrices and gates that allow us to build some quantum circuits. But this is not that easy, as we have to consider some other difficulties as no clonation due to we cannot copy qubits, or even the problem with the collapse when a qubit is measured.
Yeah, talking about the algorithms. They are already applied currently to life, as for example cryptography is. This is applied to RSA 2048, which is the method we use to pay with credit cards. This method is based into a large number that can be factorized into two prime numbers, which are impossible to find unless a quantum computer is used. Another current example is the machine learning, applied for example in autonomous vehicles. This is necessary for training machines, which leads to deep learning that aims to create a model of a user with a lot of information. With a quantum computer, this process will be simplified. The quantum simulation is another example of an algorithm which intends to simulate a physical system and emulate a quantum PC. In quantum chemistry, this allows to know information of molecules and therefore saving time. This can help in different chemistry fields, as for example in agriculture, for fertilizers, in global warming, extracting the carbon dioxide of the air molecules, or even in superconductors, in saving energy, reducing the temperature.
We need to take into account the hardware we are going to use. Current quantum computers consist of different stages, called temperature stages, which allow us to go from room temperature to really low temperatures, which are ideal for quantum computers. Here on the left, you can see what they look like. In the future, these quantum computers are going to be coprocessors because not all problems require quantum computation in order to be solved faster, so they will be controlled by a classical supercomputer. Hardware is very important in quantum technology because it can help protect the qubits, which are very fragile because they tend to decohere all the time. So, instead of using a lot of software to protect qubits, we can use hardware. However, we still need a software architecture for quantum computers. We need quantum algorithms programmed in a readable language, and we need compiled and optimized quantum circuits. The result obtained can either be sent to a quantum coprocessor or sent to a simulation backend. The simulation backends are very useful because they allow us to make much faster progress because we can test components on quantum circuits, and we can see how they behave under realistic conditions in advance of having a full quantum computer.
As a conclusion, we highlight that we will be able to solve problems with quantum computer by trying out the interference and the superposition of the qubits. Another great advantage that we can obtain from quantum computers is exponentially increasing speed to solve simulation problems of cryptography and linear algebra. However, a quantum computer will always be accompanied by a classic one, as there are functions and jobs that is capable of performing in the same time as a quantum computer would. On the other hand, other questions arise. For example, how big and fast a quantum computer must be in order to gain an advantage? What questions can we ask a quantum computer? How can we debug and compile quantum algorithms? What other problems, in addition to this discussed, a quantum computer can solve faster?
Moreover, I think that we could do a brainstorming of some questions that can appear during the process and see how can we solve them. For example, how much do we want to investigate in chemistry for future quantum applications? That way, medical field could develop further. Or doing some more tests on teletransporting coherence and its speed when traveling by a classical channel. Moreover, we also have to bear in mind if we want to look into the protection of qubits thanks to hardware used, by doing some tests on physical qubits and improving the system. And finally, and the most important question is, how much time will it take to create a 100% quantum PC, and who are the ones who are going to use it first? We don't know it yet, but one thing we have for sure is that the quantum computing is transforming the digital age. So, the Waterloo lab visit has arrived up to this point. All hands on deck, and let's continue the progress in the quantum world.